This is Dr. D. Govardhan, Professor and Head, Department of Aeronautical Engineering, Institute of Aeronautical Engineering, Hyderabad. Today, we are covering the second unit, friction, definition and terminology. Definition of frictions. When any one of the block moves or tends to move tangentially with respect to the surface on which it rests, the interlocking property of projected particles always oppose the motions. The opposing force which acts in opposite directions in which the body tends to move is called force of friction. Simply, it is called friction. That is, the friction is always acts in the directions opposite from the directions in which it tends to move. It is parallel to the surface of contact, or it is also called tangential to the surfaces. The value of frictions, it varies from 0 to limiting friction. When the body is resting on the surface, when there is no force acting on it tends to move in any directions, the friction force which is acting on the body is treated as 0. When the force increases because of interlocking properties, the body will not go, but goes on increasing the applied forces. To some instant, it tends to move in the direction of applied force. At this moment, the friction force which exists between the body and the contact surface is treated as maximum. This maximum friction force, it is called limiting friction. That is, the limiting friction is defined as the maximum friction force that can be developed at the contact surface when the body is just on the point of moving, is called limiting frictions. So, on drawing a free body diagram for the body, when there tends to move in the direction of applied force, is represented here now. The body is resting on the surface. The forces which are acting on it are now, one is the body is preventing to move in downward directions. Hence, the force which is acting in opposite directions is treated as normal reactions. The weight is acting in downward directions. Here, the force is applied to move the body toward the left hand side, toward the right hand side. Hence, the friction force is acting toward the left side as shown in figure. About to move means it is under equilibrium. That means the normal reaction is always equal to the weight of the body. The force which is applied tends to move the body toward the right side is equal to the friction force. Since it is about to move, the friction force which exists is called limiting friction. Types of frictions. Here these are classified as now static friction. The friction force experienced between the body and the contact surface when it is at rest is called static friction. When the applied force is equal to 0, then the static friction is also equal to 0. But this static friction values increases when the applied forces on the body increases to move in the directions. When it is about to move, that is called maximum limiting friction. Since the body is at rest, the friction force which experiences between the body and the contact surfaces up to the limiting friction comes under static friction. Dynamic frictions, the friction experienced between the body and the contact surfaces when it is in motions is called dynamic frictions. Sliding friction, the friction experience between the body and the contact surfaces when it slides over it is called sliding friction. The rolling friction, it is the friction force experienced between the body and the contact surfaces when the body is rolling over the surfaces. Coefficient of frictions. Here I am taking the object now, which is resting over the surfaces as shown in figure. A P force is applied on the body to move toward the right hand side as shown in figure. When the body is about to move, the frictional force experienced between the body and the contact surface is called limiting friction. It is treated as maximum values. Here it is acting toward the left hand side as shown in figure. The forces which are acting on the body are, one is the weight, it is acting in downward directions, and N is representing normal reactions, F is the applied force, and F is the frictional force. When it is about to move, the frictional force which is experienced is treated as the maximum values, which is equal to the applied force P now. The weight is now balanced by the normal reactions. The coefficient of friction is defined as it is the ratio of frictional force to the normal reactions. That is mu is equal to F by N now, where mu is equal to coefficient of friction, F is the frictional force experienced between the body and the surface, and N is representing the normal reactions. The angle of frictions. Here, the resultant of frictional force and normal reactions is represented here R. Assume this is nothing but R is representing the resultant of frictional force and normal reactions, which is making inclination with the vertical as shown in figure. The angle of friction is defined as the angle made by the resultant of friction force and normal reactions with the normal reactions, or in other words, it is the angle between R and N now, where R is treated as a resultant of friction force and normal reactions, and F is the friction force now, N is the normal reactions. Angle of repose. Here, assume the body is resting on a plane now, as shown in figure. By keeping one end is in fixed position, the other end of the plane is moved upward directions, that is called here tilting. Even though there is no applied force on it, but at a certain angle, the body tends to move in downward directions. The angle at which the body tends to slides downward directions without application of any external forces on it, the angle is called angle of repose. Here the angle of repose can be defined as the maximum inclination of the plane on which the body, free from external forces, can repose. Repose means sliding downward directions. It's called angle of repose. Okay, at this position now, the forces which are acting on it are called, here now, the weight is acting always in downward directions. Here, N is representing the normal reactions. F is representing the frictional force. Since the body tends to move in downward directions, the frictional force always acts opposite directions, in which direction the body tends to move. And after resolving, since there is no external forces acting on it, these forces can be resolved into two components now. That is W sin theta, W cos theta. That is now when it is about two movements, the body is in equilibrium position under frictional force, normal reactions, and the components of weight of the body now. When the result in the forces normal to the plane now, that is N is acting upward directions, W cos theta is acting downward directions, both are equal in magnitude and acting in opposite directions, hence we can take it as N equal to W cos theta. Similarly, the forces which are acting along the plane, the frictional force is acting toward the right hand side, and the component of weight W sin theta is acting in downward directions, both are equal in magnitude and acting in opposite directions, hence we can take it as F is equal to W sin theta. Dividing equation 1 by 2, we got F by N is equal to tan theta, here tan theta, or which is also equal to tan pi now, where pi is the value of theta. When the motion is impending, the friction force will be the limiting friction, and hence tan pi is equal to F by N now. Thus, the angle of repose is the same as the value of limiting angle of friction. Cone friction. Here, when the body is about to move toward the left side on a horizontal plane because of application of F40P as shown in figure, the forces which are acting on it are frictional force and normal reactions and W now. Here, R is representing the resultant of frictional force and normal reaction, which is making an angle of alpha as shown in figure. The direction of resultant force is always it tilts at a certain angle so that it can prevent the motion of the body. But when the direction of applied forces, when it changes from 0 to 360 degrees, the resultant force also changes its direction 0 to 360 degrees now. That is, the application of the force is the same now, but the tail of the resultant force, it traces the right circular cone as shown in figure. It depends upon the direction of rotation of the forces. From 0 to 360 degrees, it is also rotate. It forms that is called locus in the form of right circular cone as shown in figure. The diameter of the radius of the base of the cone, it is equal to the friction force. The height of the axis is representing the normal reactions, and the length of the slant, that is generated, is equal to the resultant of friction force and normal reactions. So, this is called here now cone friction now. That means when the applied forces, when it changes from 0 to 360 degrees, the resultant force traces a right circular cone as shown in figure. This is called here now cone friction. Here, when a body is having impending motions in the direction of P, the friction force will be the limiting friction, and resultant reactions R will make limiting friction angle with the normal reactions as shown in figure. If the direction of the force P is gradually changed through 0 to 360 degrees, the resultant R generates a right circular cone with a semi-central angle equal to the alpha. This inverted cone with a semi-central angle equal to the limiting friction angle is called cone of friction. Coulomb's law of dry frictions. Here the dry frictions itself is representing the contact surfaces not at all having any lubrications. So in these conditions, when the body is about to move over the horizontal surfaces, which is in dry conditions, that is certain laws are here discussing. The first one is the frictional forces are always above the motion of the body. It acts in opposite directions in which the body tends to move or the moving up. And the applied forces when it is 0, the friction force is also equal to 0. And when the applied forces increasing gradually, the friction force experienced between the body and the contact surface also increases. When the body is about to move, it is having maximum frictional force, which is called limiting friction. That is the value of frictional force which is reached limiting value. The magnitude of frictional force is exactly equal to the tangential force which tends to move the body. The magnitude of the limiting frictions bears a constant ratio with the normal reactions between the body and the contact surfaces. The force of frictions depends upon the roughness and the smoothness of the surfaces. When the body is moving over the surfaces, the frictional force is called dynamic frictional force, which is slightly lower than the limiting friction values. The ratio is called the ratio of frictional force to the normal reactions when the body in motions is called dynamic friction. Equilibrium of a body on a rough inclined plane subject to a force acting horizontally. Here, the body is resting over the an inclined plane which is making an angle of alpha with the horizontal as shown in figure. Let P be the force which is acting horizontal so that the body tends to move upward directions or downward directions. Here it is preventing its motions in downward direction. That means the inclination of the plane is greater than the angle of repose or limiting angle of frictions. When we are taking alpha is greater than pi now, that means without the application of the force, the body tends to move in downward directions. Hence, the P1 is the force that is treated as which is preventing its motions in downward directions. So it is now equilibrium positions now. In these conditions now, what is the minimum value that P is required now? Which is given by resolving the forces along the plane as well as the perpendicular plane. And simplifications we got P is equal to W into tan alpha minus pi values. That is the minimum force that is required to keep the body in equilibrium position to preventing to slide in downward directions is given by W into tan alpha minus pi, where alpha is the inclination of the plane with the horizontal and pi is treated as the limiting angle of friction. Similarly, equilibrium of a body on a rough inclined plane subject to the force acting horizontally In the previous case, we have taken the force P is applied to prevent its motions in downward directions. Here we are taking that P is the minimum force that will keep the body in equilibrium when it is at the point of sliding upward directions. That is, the friction force is acting in downward directions, P is acting upward directions. It results into two components, and N is representing normal reactions and W is representing its weight now. It is result into two components as shown in figure. From this one, we got the minimum force P given by W into tan pi plus alpha values. Okay, application of frictional force. So here we are having applications of frictional force in ladder, wedge as well as the screw now. Hence, the friction force which exists in between the ladder, it is called a ladder friction. Between the wedge and the surface, it is called wedge friction. Between the screw as well as the nut is given by screw friction now. Okay, these are the just a few applications here we are discussing now. Ladder friction now. Assume just here ladder is kept against the vertical wall as shown in figure. Assume these are the rough surfaces. The forces which are existing on the ladder are given by here A and B is assumed just representing the ends of the ladder. At A point, here the weight is acting now. The forces which are acting on it are one is the weight of the ladder. Since we are taking it is having uniform cross section, the weight is always passed through the center of the ladder now. When the person is climbing this over the ladder, at certain points, it tends to slide downward directions. It depends upon the surface roughness of the contact surfaces. Here the forces which are acting on the ladders are given by at a point 2. One is the friction force, which is always acts toward the vertical wall as shown in figure, because it is preventing the sliding of ladder toward the left hand side as shown in figure. And NA is representing the normal reactions at A. W is representing the weight of the body. At B point, the friction force is there now. That B end tends to move in downward directions. That is the friction force that acts upward directions. And the normal reactions at B, that is the NB, it is a perpendicular to the contact surfaces. So they should somewhere assume W it is there now, M, that the weight of the person is there at certain point from A position. When it is about to slide in downward directions, that means all these forces are in equilibrium conditions. That means the sum of the forces acting in horizontal directions also equal to 0. The algebraic sum of the component of vertical forces should be equal to 0. Since the forces are parallel to each other now, hence the moments created by the forces at any point should be equal to 0. Okay, these three conditions are satisfied. By using these conditions, we can determine what is the friction force that is existing between the contact surfaces and how much force that friction force should be required in order to prevent the sliding of ladder downward directions. Here, after resolving the forces along the horizontal directions, the forces which are acting on it are after resolving the forces along the x directions, since the body is about to slide, that means it is a static equilibrium. The parallel forces are acting on it. Three conditions should be satisfied. The first condition is that the sum of the component of forces acting in horizontal direction should be equal to 0. That means sigma fx is equal to 0. The horizontal component of forces here, Fa is acting toward the left hand side and Nb is acting toward the left side and Fa is acting toward the right hand side. Both should be equal in magnitude and acting in opposite directions. The sum should be equal to 0, or in other words, Fa minus Nb is equal to 0 now. Generally, while taking algebraic sums, the forces which are acting toward the right hand side are treated as positive and the forces which are acting toward the left side are treated as the negative. Similarly, the algebraic sum of the vertical components which are acting on the ladder should be also equal to 0. Here, Na is acting upward directions, Fb is also acting upward directions now, and Mg is acting in downward directions. So in this case now, here now, Fb positive plus Na is also positive minus W should be equal to 0 required now. And the third one is the moments created by the forces at any point should be equal to 0. The preferable points are A or B. When I am taking this moments at a point A, I am taking this is nothing but treated as the MA. That is MA is equal to, it should be equal to 0 required. That means MA into here now, FB into perpendicular distance is given now. It is nothing but here B. Similarly, NB it is there now. It is nothing but H. Both are tends to rotate the body in anti-clockwise directions. These anti-clockwise movements are treated as here the positive, and weight is there. It is acting downward directions, tends to rotate the body in clockwise directions. It is a theta negative. It is equal to mg into this angle is given theta, that is mg into L by 2 into sin theta. It should be equal to 0 required. So, by using these conditions, we can determine what are the forces that are acting on the ladder. How can we determine the forces Fa as well as the Na? And in order to prevent its motion downward direction, so what is the just frictional force that is required? That nothing but generally it depends upon surface roughness. Is how much is required we can determine. The second application is application of the friction in wedge. It is called wedge friction only. Wedges means it is a small piece which is in the form of triangle or trapezoidal in cross section. It is used to either lifting the loads or lowering the loads. Okay, application of the friction in wedges. Wedge is a small piece, no, which is in the form of triangle or triplet section. It is made up of wood or piece of metal. The main application of the wedge is it is used in industries now to lift heavy loads smaller distance for making adjustments in assembling the parts. While lifting the heavy loads, the wedge is placed at the bottom of the load and an horizontal force P is applied repeatedly by blowing so that when the wedge is moving toward the left hand side, the load moves in upward directions. Okay, analysis of forces on the wedge. This analysis can be done by using equilibrium method. In equilibrium method, the forces are resolved along the wedge, that is inclined plane, and perpendicular to the wedge surface, as well as at the surface contact. Again, it can be resolved parallel to the surfaces. So, after resolving the forces along the inclined plane, we can determine what is the minimum force that can be applied over it to move the body in upward directions. The second method is Lemi's method is also applicable now. According to the Lemi's method, when the three forces are acting simultaneously in the body, when the body is in equilibrium position, each force is always proportional to the sine of the angle between the other two forces. Already we have taken P, Q, R are the forces which are acting simultaneously. Here now, here we are taking here one force, one more force, another force is there now. It is a P, it is a Q, and R it is there now. Here this angle is nothing but alpha, beta, and gamma. These are the angle between the two forces we have taken. According to the Lemi's theorem, P by sin alpha is equal to Q by sin beta is equal to R by sin alpha. It should be constant now. So, by using these conditions, we can determine the minimum force P that can be applied over the body to move, to lift the heavy load now. So, the forces which are acting on the wedges are here represented as, here the body it is there now. This is the wedge is there. The force is applied like this now. Here it is the contact surface is there. The body has to move upward directions. Hence here the frictional force is acting downward directions. Here the normal reactions now. As in this is nothing but A point, first one, N1, and frictional force is nothing but area F1. Here the body is nothing but when it is moving with respect to the object now, it is moving upward directions now. This is along the surface. Hence the frictional force is acting here now for downward directions, and it is the normal reactions now. Here contact surface is there now. Again here normal reactions now. Since the body wedge is moving toward the left side now, the friction force is acting in opposite direction. So this is nothing but 2, 3 and F3 we are taking now. So here we are taking the forces which are acting first on the body. Here it is represented A. The second one is at B, we have to take it now. So the forces between the wedge and the surface of the ground now. We have to consider the force P is applied horizontally. Here it is the force P is applied now. The reactions N1 and face AC and friction force F1 now. The forces between the wedge and the load is given now. The normal reactions N2 and phase AB is given now. And frictional force F2 is also given now. So, by using these conditions resultly, we can determine the minimum force that can be applied in order to lift the load. This is one of the application of the frictional force now. The third application is screw jack now. That is screw friction. The application of the screw friction is the one device is made. It is called simple screw jack. Simple screw jack is used to lift the heavy loads by applying lower load at the end of the lever as shown in figure. The main component of the screw jacks are now, one is the screw, which is having square threaded rod as shown in figure now. It is there. And the body is there now. The body is having integrally a nut just provided inside it now. Here, at the top of the square threaded rod, one head is also there. And at the top again, one here cup is also provided over it now. The cup is there, just it can be rotated freely over the end of the square threaded rod as shown in figure. By using the lever, this is head of the rod is provided 4 slots now given to insert the lever as shown in figure. By inserting, the rod can be rotated in clockwise direction or anti-clockwise directions, depending on the load can be raised or lowered now. Okay, the main parts of the simple screw jack are square threaded rod as shown in figure now. One is the nut. It is again sometimes it is the integral part of the body. Head of the screw with the bolts is also provided. Collar is provided at the top. It is in the form of cup to keep the load over it now. And it can be rotated freely with respect to the pin projected at the top, so that when the nut is rotating, the load should be in stationary. And lever is also provided to rotate the nut now. The load raising by using screw jack, it is similar to the pulling the load over the inclined plane now. For one complete revolution means the load is raised from at a distance of approximately just pi d circumference of the circle. That is, when it is moving a distance of pi d, that circumference of the circle, the load is raised an height of p as shown in figure. That means the inclination of the plane is given by the tan alpha is equal to p by pi d now, where d is representing the diameter of the mean diameter of the screw now. P is equal to pitch of the screws. So the minimum force that is required to raise the body is given by the equations now. It is given by P equal to tan alpha plus by, already we have completed these equations in inclined friction now. That is P is equal to W into tan alpha plus pi. But this P is nothing but applied at the end of the screws. It is having a turning effect, that is, it will rotate the body. But actually the force is applying at the end of the lever. That is, the screw jack is there now, head is there, here, at a distance of L, it is applying now. But this P force is applying at a distance of D from the center. It is there now, D by 2. Hence, we are having the moments created by the force which is applied at the end of the lever should be equal to the moments created by the force P at the surface of the screw now. By using these relations, it can be written as the torque developed at the end of the screw is given by P into D by 2, that is equal to W into tan alpha plus pi into D by 2 now. Similarly, the force which is applied, as in P1 is the force applied at the end of the lever, the torque developed is equal to P into L by 2 L by 2. So, which is equal to, that is P1 into, that L should be equal to, we can write it as W into tan alpha plus pi into T by 2 now. So, sometimes the friction resistance also exists in between the collar as well as the nut also. When we are considering the total torque is given by P into D by 2 plus mu into W into R now. So, by using the relationship, we can determine what is the torque that can be required to raise the load for one revolution. So, in upward directions can be determined by the equation P into D by 2 into plus mu1 into W into R now. For lowering the load, alpha minus pi now. So, by using these equations, we can determine what is the, it should be torque that should be equal to P into L. By using the equations, what is the minimum force that can be applied at the end of the lever can be determined. The mechanical advantages. Generally, briefly, it can be written as now, MA is the ratio of weight lifted to the effort applied. That is the, mathematically, it can be expressed as W by P now. The second definition, velocity ratio, it is the ratio of the distance moved by the effort to the distance moved by the load. So, mathematically, the load is nothing but applied load is rotating now, which is applied at the end of the lever. Hence, the distance moved by the load is equal to 2 pi L. After completion of one revolution, the load is moved upward direction a distance of P, that is the pitch of the screw. So, the distance moved by the effort to the distance moved by the load, it is called velocity ratio, which is equal to 2 pi L divided by pi now. Or 2 pi L, it is equal to tan alpha into pi d. From this relation, we got to 2L divided by tan alpha into d now. So, mathematically, by using the two equations, the efficiency of the screw jack is given by mechanical advantage divided by the velocity ratio. N, which is equal to W by P, and it is a mechanical advantage, that is the load lifted to the effort applied, divided by velocity ratio, the distance moved by the effort to the distance moved to the load. On simplification, we got W by P, which is equal to now divided by 2L into tan alpha into D now. Okay, the differential screw jack, generally it is used to lift the heavy loads when compared to the simple screw jack. It consists of two screws now. One is just having integral, it is having combinations with the body of the screw jack with the outer screw. Within the outer screw, again, internally, that threaded are provided to it now. And the load is applied just over the internal thread, over it now. Generally, it is used to lift the heavy loads when comparing with the simple screw jack. Okay, these are the references to be followed for the definition terminology of second unit, the friction.
Like, share and subscribe. hit the bell icon for more updates.